All right, today we're diving into something pretty cool, a blueprint for seeing through digital noise. It's a whole process for taking a blurry, messy image and making it absolutely crystal clear. And the really wild part, it doesn't use some crazy new tech. It actually uses a bunch of classic, simple tricks that, when you put them together, do something incredibly powerful. So let's get into it. So let me ask you this. What happens when the most important detail in a picture is just gone, lost in all that digital static? It's like trying to solve a puzzle, but half the pieces are just a blurry mess. Think about it. What if a doctor can't see the exact edge of a tumor? Or an analyst can't pick out a key landmark in a satellite photo? Yeah, the stakes get really, really high, really fast.
And listen, this isn't just some academic thought experiment. This is a real-world, critical problem. You're looking at just a few of the fields where getting a clear image is everything. We're talking medical imaging, remote sensing, surveillance, places where one blurry detail can lead to a completely wrong conclusion.
Okay, so let's dig into the core of it all. At the end of the day, the problem really does come down to the pixels themselves.
When an image is full of noise or the contrast is all washed out, the information you're trying to get from it becomes, well, totally unreliable. And that's the scary part, right? It's that classic garbage in, garbage out problem. If the picture you start with is junk, any analysis, any conclusion you draw from it is going to be junk too.
But the good news is, super smart people have been tackling this for a long time, and the paper we're looking at today proposes this really elegant, engineered solution.
And here's what I love about this approach. This isn't about some magic filter you just slap on an image and hope for the best. No, it's a multi-stage pipeline. It's all about taking several proven, almost old-school techniques and making them work together in a very specific, very clever way. The whole is way, way greater than the sum of its parts.
All right, let's pop the hood and see how this thing is actually built. We're going inside the image pipeline, step by step.
So here's the roadmap. There are 5 main stages, and it kicks off with something that sounds completely backward. Step 1 is actually injecting noise. I know, right? Why would you add noise to a noisy image? Well, it's actually genius. It standardizes the input, so no matter how bad the original image was, the rest of the pipeline gets a consistent, predictable starting point. From there, it filters that noise back out, cranks up the contrast, finds the important edges, and then finally cuts out the main subject. Every single step perfectly sets up the next one.
So that first big step is called median filtering. Now, a lot of filters work by averaging the pixels around a certain spot, but that tends to blur everything. The median filter is smarter. It looks at a pixel's neighbors and picks the middle value, the median. And this is so effective because it wipes out all those random specks of noise, you know, the salt and pepper static, but it keeps the important edges of objects nice and sharp.
Okay, next up is a real mouthful, CLHE. Don't even worry about the full name, just focus on what it does, because it's brilliant. See, a normal contrast tool just brightens up the whole image at once, and that can blow out the details. CLHE is different. It's like a tiny artist that goes through the image, section by section, and adjusts the contrast just for that little local area. The result? You get these incredible details popping out in both the super dark and the super bright parts of the picture.
So now we've got a clean, high-contrast image. The next job is to actually figure out what's in it. The system uses a couple of classic algorithms, Sobel and Canny, to find all the key boundaries. You can think of them like digital sketch artists, tracing all the lines where there's a sharp change from dark to light. This is how the computer starts to see the shape of things.
And that leads us to the final step, segmentation. After all that prep work, the system can finally make a simple choice. For every single pixel, it asks, is this part of our main subject, or is it just the background? It creates this clean, black and white mask that perfectly isolates the thing we want to analyze.
Okay, that all sounds fantastic on paper, but does it actually work? And more importantly, does it work better than other methods? This is where the real science comes in. It's time to put the process to the test.
So the researchers set up a classic showdown. In one corner, you have the common Gaussian filter, and in the other, our contender, the median filter. The goal was simple. Which one does a better job at that crucial first step of cleaning up the noise?
And the results are in. We're looking at 2 key scores here, PSNR, which measures overall image quality, and SSIM, which checks how well the structure of the image is preserved. In both cases, a higher number is a better number, and you can see it right there. The median filter is the clear winner on both fronts. Now, looking at the raw numbers is one thing, but this bar chart really drives it home. It's not even close. The median filter gives a significantly better performance in both preserving the quality and the structure. The data is practically shouting at us here.
And the paper just nails the conclusion. It says, flat out, that the median filter is just better at preserving edges. And that's the whole game, isn't it? By getting that first step right, by keeping those edges sharp, it sets the rest of the pipeline up for a huge win.
Okay, so the tech works, it's proven, but let's zoom back out. Why does any of this matter in the real world? What's the impact?
Well, here's what this process really achieves. First, you get way more accurate segmentation. The computer is just better at finding the thing it's supposed to be looking for. Second, there's less distortion, so the shape of that thing stays true. And maybe, most importantly, you hang on to those tiny, critical details that are so easy to lose.
Think about it like this. For a doctor looking at a medical scan, this isn't about making the picture look a little nicer. This could be the difference between seeing a blurry, questionable spot and seeing a crisp, clearly defined lesion. That level of clarity, it can change a diagnosis. It can change a patient's entire course of treatment.
And that same idea applies pretty much everywhere. For an analyst looking at satellite photos, it means being able to confidently identify a vehicle versus, a rock. For a surveillance system, it means being able to track a target accurately even in a grainy, low-light video. Bottom line, it makes our tools smarter and the information we get from them far more reliable.
And get this is probably just the start. The researchers are already looking ahead. They're talking about integrating modern deep learning and AI into this pipeline. Just imagine a system that doesn't just clean the image, but actually learns what parts are important and pays extra attention to them. It could make this whole process faster, smarter, and even more powerful.
And that leaves us with a pretty fascinating question to chew on, doesn't it? Right now, we're teaching computers how to fix the imperfections that we notice, the blur, the noise. But what happens as these systems get smarter and smarter? What new hidden imperfections will we ask them to find next? What patterns are hiding in our images that are totally invisible to the human eye, just waiting for the right algorithm to uncover them?